So good day. So in the last lecture we discussed about creep. We have done experiments related to creep and this spring experiment. And from this spring experiment, it is clear that for a material with this ratio, room temperature versus melting point ratio, if it is greater than 0.5, then that material will subject to creep, okay, or the elongation and fracture because of creep. And this is the definition of creep. And from the definition, it is clear that the creep process is a time-dependent process. Okay. So for the any creep deformation or creep fracture, there is a need of time. Okay, this is not a sudden process. Creep deformation is not a sudden process like a fatigue. It is a time-dependent process. Okay, and it is a followed with a plastic deformation. It is not an elastic deformation process. Creep is a plastic deformation process. Okay, so that is the next point regarding about this creep. It is a plastic deformation process. And here in this creep deformation, we are not changing the load acting on the member. So it is a constant load process. Okay, it is a constant load process. That is the third point. And it is actually happen at the elevated temperature. So these are the four important points related to creep. It is a time-dependent process. It is actually it is a slow process. Okay, it is not a sudden process. And during the creep deformation, there will be a plastic deformation, and it happened during the constant load process. Okay, we are not changing the load for creep deformation. When a body or member subjected to constant load, there is a chance for this type of creep failure. Okay, and this happened at the elevated temperature. So these are the four important points of the creep fracture or creep deformation. And we discuss about the temperature, influence of temperature for creep failure. And if the temperature is significant when the temperature of the atmosphere or temperature of the material is greater than that of the 0.5 melting point of that material. Okay, so when we compare this aluminum and tin at room temperature, for aluminum, this ratio, this room temperatures versus the melting point ratio is only 0.32, but for this tin it is 0.66. That is why during this experiment, tin elongated after tin lead material alloy elongate after 5 minutes, but there is no change in the length of the aluminum after 5 minutes. Okay, so this ratio is less than 0.5 for aluminum, but for this tin lead alloy, it is greater than 0.5. That is why this creep deformation happen in the second spring. Okay, so that is the effect of temperature. And as well as other than temperature, the stress also an influencing factor for creep. Okay, so during the creep deformation, we are applying constant load, but that load is also a significant factor which affect the creep deformation. Okay, so here in this graph, we can see the influence of temperature and stress acting on a material. Okay, so here in this, we can see when the temperature is less than 0.4 melting point, after a particular amount of strain, so this is the strain, creep strain. So here we can see in this orange colored graph, after a particular amount of strain, then it is a constant one. Okay, there is no change in the strain with respect to time. That means after this initial strain, what happened? The material gets strain hardened. Okay, we already discussed what is strain hardening. Okay, so after this this much amount of strain, the material is strain hardened, so the materials become stronger. So further strain is not happen when the temperature is less than 0.4. We can say 0.4 or 0.5. Okay, when the temperature is less than 0.5 of melting point. Okay, so there is no such a creep deformation happen when the temperature is less than 0.5 times of melting point. But when the temperature is greater than this value, or the stress value is higher, then this is the graph. Okay, so here we can see T3 is greater than T2 greater than T1. Similarly, stress sigma 3 sigma is greater than sigma 2 greater than sigma 1. So here we can see when the temperature and the stress values acting on the member is increased, correspondingly the strain rate also increased. That means the material become rapidly deform plastically. Okay, so here we can see in this red colored graph, with a very less amount of time, there is a huge strain deformation or plastic deformation happen in this material. But here in this we can see the a medium amount of time is taken for the deformation, and here a low amount of time is taken for the deformation. So the temperature and stress acting on the material or load acting on the material directly influence the amount of strain developed on a material under creep deformation. Okay, so these are the two important factors which affect the creep deformation: the temperature as well as stress. Okay, so we have for a material, we should maintain a lower temperature, and the temperature should be less than that of the 0.5 times of the melting point, and as well as we should maintain a lower stress acting on the material to avoid any type of such a creep deformation and a creep failure. Okay. Next, we are discussing creep care, and they are like a stress strain curve. We already draw a stress strain curve for different ductile and brittle material. This is a stress strain curve. Okay, and similarly for a creep deformation, we have a creep curve. Okay, so this is the creep curve. In the creep curve, we use time as the x-axis and the strain, creep strain in the y-axis. Okay, this is the x and y axis of a creep curve, and this is the creep curve. Mainly, this is the shape of a creep curve. Okay, and this creep curve can be divided into three regions. This is the first region called the primary region. This is the first region called primary region, and this one is the second region called secondary region, and this is the third region called tertiary region. Okay, and finally after tertiary region, the material is ruptured. So this is the rupture point. Okay, so initially there is a strain, and this strain is called instantaneous deformation strain. Okay, this is instantaneous deformation. This is instantaneous deformation. Okay, so when time is equal to 0, there is an instantaneous deformation at time equal to 0. With respect to increase in time, what happened? The strain also, creep strain is increased, and finally leads to rupture of the material. Okay, so in this we divide into three regions: primary, secondary, and tertiary strain regions. Okay, and what is the difference between these three regions? We can see in this region, the strain rate is very high. Okay, the amount of creep strain rate is very high in the primary region. And after the primary region, we can see in the secondary region, the strain is a almost steady state. Okay, this is a steady state. That means the slope is almost horizontal. Okay, compared to these two regions, primary and the tertiary region, the secondary region slope is very small. So we can say that is a steady state creep region. And the third region is again, the strain rate is very high, the slope is very steep. So that is also a high rate or high strain rate region. That is the tertiary region. After tertiary region, we can see the rupture point. Okay, so the strain rate is very high here, it is very low here, and here it is also very high. Okay, that is the creep curve. Okay, so the strain rate is expressed d epsilon divided by dt. That means strain with respect to time. D epsilon is strain, so d epsilon by dt is the strain rate. So strain rate is higher in case of primary and tertiary stage, but it is very small in case of secondary stage. Okay, that is the creep curve. And what are the different reasons for these three regions? And what happened to the material in these three regions? We will discuss about that. So, the first one is the instantaneous deformation region. This is the instantaneous deformation region. At t equal to 0, we can see some amount of strain. Okay, this is not zero strain. So there are some strain in the material at time t equal to 0. So that amount of strain is called instantaneous deformation strain, which is mostly elastic. That means when we release the load, it will come back to its initial shape and size. Okay, so the resulting curve consists of three regions. After instantaneous deformation, we have three regions. We already discussed that. The first region is called primary or transit creep region. And what happened during in this region? There is a continuous decrease in the creep rate. Okay, and that means the slope is actually diminished with respect to time. Okay, so this suggests that the material is experiencing an increase in creep resistance or strain hardening deformation become more difficult as the material is strained. So that happened during the primary region. So in the primary region, so when I apply a constant load on this material, initially there is an instantaneous deformation, a small increase in size for the material. That is the instantaneous deformation. Okay, and after instantaneous deformation, I'm not increasing the load, but under this constant load, again there will be a sudden increase in the material length or material size. Okay, so this is the primary region of the deformation curve. Okay, so there is a sudden change in the size and shape of the material. So that is the primary region. And during this deformation, during this primary deformation, what happened? The length or size is increased by a large amount, and during this time there will be a strain hardening. Okay, there will be a strain hardening. The dislocation density will increase, and this dislocation density retard the movement of dislocation along the slip planes. Thereby, the strength of the material increase by this in this stage in the primary region. That is why after during the initial stage of primary region, we can see a huge strain increase, or strain rate is increased in a rapid rate in the primary region. But after reaching the middle area, we can see the strain rate is decreasing. Okay, and this decreasing, that means the slope is decreasing. Here we can see the slope is very high or steep in this region, but here in this region of primary region, the slope is decreasing. The decrease in slope is because of this the strain hardening. Okay, by strain hardening, the strength of the material increase. So further, for the further strain, we need to apply more amount of load on this material. So actually in the creep deformation, we are not further increase the load. So we can say there is a decrease in the strain rate in the last regions of the primary area. Okay, so that is about the primary region. Then we can see the secondary region, and again the strain, because of the strain hardening, again the further deformation will be very difficult. Okay, so in the secondary region, the strain rate, the rate of strain will be very low. Okay, so that is the secondary region. So for the secondary creep, sometimes called, it is called steady state creep, because we can see in this curve, it is almost horizontal. Okay, it is not very steep. So we can say this is a steady state creep region. The rate is constant here. Okay, it is almost linear here. And what happened during this? It is a long duration stage. Okay, it will take very long time for this, for the completion of this secondary strain region. Okay, primary and the tertiary regions are very short, but it is a long duration stage. Okay, and what happened during this stage? The balance between completing process of strain hardening and recovery is happened during this stage. Okay, so the strain hardening started in the end of the primary region, and in the secondary region, mainly the strain hardening is the reason for the decreasing the strain rate. So here strain rate is decreased. The main reason is the strain hardening and the recovery of the material. Okay, and after at the end of the secondary region, material again softened. Okay, so in the secondary region, initial stage of secondary region, materials was very hard and very strong, but at the end of the secondary region, after a long time, at the end, the material becomes again soft. Okay, so that is the secondary region, and that is the material microstructure change during the secondary region. And third region, that is called tertiary region, and during the in this region again the strain rate is accelerated. Okay, we can see an acceleration in the strain rate, and the curve is very steep. Okay, and what happened during this stage? Rupture and resulting from the microstructure and metallurgical change. Okay, during this stage we can see the formation of necking regions, and cavities and voids etc. are formed during this in this tertiary region. And finally, the crack is propagated and leads to the failure of the material. Okay, so this is very steep curve, the third region. Okay, so these are the three regions of the creep curve. Okay, so from the starting of load to the ending of rupture, we can see three regions. In the primary and the tertiary regions, the strain rate is very high, but in the secondary region, it is almost steady state strain rate increase, or we can say the strain rate is very low in the secondary region. Any doubt? ആർക്കെങ്കിലും എന്തെങ്കിലും ഡൗട്ട് ഉണ്ടോ സ്ട്രെയിൻ ക്രീപ്പ് കർവിനെ കുറിച്ച്? ഓക്കെ ആണോ? Okay, so that is about the creep curve. Next one is creep test. So for drawing this creep curve, we are conducting a creep test. Okay, so what are the different factors we are considering while doing this creep test? So these are the four factors. It is a time dependent process. So during the creep test, we have to measure the time and what are the effects in different time intervals. Okay, then there will be a plastic deformation. So we should measure the plastic deformation during the creep test, and during the creep test we should provide constant load, because creep deformation is happened in the constant load, under constant load. So we should provide constant load during the creep test, and we should provide a elevated temperature atmosphere around the sample during the creep test. Okay, then only this test meet the requirements of the creep deformation. Okay, so this is the arrangement used for creep test. So in this creep test, this is my specimen, and the specimen, it is a standardized specimen, and the specimen actually this is a almost similar specimen which is used for UTM test. Okay, and this specimen is hauled between these two grips, and in this grip we provide a constant load. The load will not vary during the test process. Okay, and here around this specimen we provide elevated temperature, and we can use any type of furnace for conducting this test. Okay, so this is the creep test arrangement, and this is a figure showing the creep test. And in this creep test, to measure the elongation similar to the UTM test, we can use the gauge length and the measurement device. What is the measurement device used to measure the gauge length variation? Anyone? എന്ത് മെഷർമെന്റ് ഡിവൈസ് യൂസ് ചെയ്യുന്നത്? UTM ടെസ്റ്റിൽ എന്ത് മെഷർമെന്റ് ഡിവൈസ് യൂസ് ചെയ്തേ?
Extensometer.
Yeah, extensometer is used. So similarly here we can use extensometer. We can use a manual extensometer or laser type or computer type extensometer can be used to measure the variation in the gauge length under the application of constant load. The main difference between the UTM testing and this creep test is that in UTM testing we vary the load. We increase the load applied on the specimen gradually, but here with respect to time, we are not vary the load applied on the specimen. It is a constant load process. Okay, so we apply a constant load on the material and we provide a high temperature atmosphere around the specimen. Then we measure the variation in the gauge length with respect to time. Okay, and this is the arrangement used for creep test. And this is the creep test of an aeroplane component. And in this aeroplane, this is the engine, and this is the turbine, and this one is the turbine blade. And this turbine blade actually subjected to creep deformation and creep failure. Okay, so we can measure or we can conduct a creep test on this turbine blade. So we made a standard specimen using the turbine blade material, and we provide a heated atmosphere, hot surface atmosphere around the specimen, and we conduct the creep test. Okay, so after with respect to time, we increase, we maintain a constant temperature. We are not changing the temperature. At a particular temperature, we kept the specimen under constant load, and we check the variation in the size of the specimen. Okay, so this is the resulting graph, that is the creep curve from the creep test. Okay, so it's almost similar to the our spring experiment. It's almost similar to our spring experiment. In the spring experiment, we are not providing any elevated temperature. We conduct the spring experiment at a room temperature. But in case of lead tin alloy, the room temperature is actually an elevated temperature. Okay, so we conduct this similarly. This is almost similar experiment, creep test or creep experiment. Okay, so from the creep test, we can plot this creep curve, primary, secondary, and the tertiary creep curves. Okay, so the procedure is the unload the specimen is first heated to a required temperature. So we maintain a constant temperature, and the gauge length is measured, and the predetermined load is applied quickly without shock. So we are applying a constant load without shock. So that is very important criteria. And measurement of extensions using any type of extensometer, we can measure the extension at frequent intervals. Okay, and average 50 readings is taken for measuring the or for plotting the creep curve. So that is the creep test. Any doubt about this creep test and creep curve? Okay. Doubt in the creep test and creep curve. നിങ്ങളൊന്ന് റെസ്പോണ്ട് ചെയ്യേ. ഓക്കെ ആണോ?
ഓക്കെ സർ.
Then structure change during creep. What happened to the interior or the microstructure of the material during the creep deformation? Okay, so we provide a constant load on this material, and we provide a elevated temperature around the material. Okay, so what happened inside the material? So this is a, for example, this is a polycrystalline material. a polycrystalline material. What happened to this material microstructure during the creep deformation? Okay, so that is structure change during the creep deformation. So when we plot the creep curve in terms of this creep rate and strain, creep rate and strain, we can see the primary stage. In the primary stage, the strain is creep rate is very high. Okay, primary stage. So again I am plotting this. I am plotting this another curve. The first one is the creep rate, d strain divided by dt. Okay, and here this is the total strain. Okay, so in the primary area, the creep strain is very high. Okay, then creep strain is goes on decreasing from with respect to time. Okay, so here it is very steep, it is almost steady. So that means creep rate is decreasing. So that is showing here the creep rate is decreasing or strain rate is decreasing. Okay, and this is a steady state region. Almost the rate of strain increase is almost constant. That is showing here almost constant creep strain rate. It's almost constant. And after this, in the tertiary region, again the creep rate is increasing or the strain rate is increasing. So that is showing here. Okay, so this is the primary area, and this is the secondary area, and this is the tertiary area. Okay, and in this creep rate change is because of the change in the internal structure of the material. Okay, so from the starting to ending, we can see the variation in the creep state. Here in the creep rate is decreasing. Here in the second stage, creep rate is almost constant. And in the third stage, the creep rate is increasing. So this variation is because of this structural internal change. Okay, so what are the different things happen in the structure during these three stages? First one is deformation by slip. Second one is subgrain formation, and third one is grain boundary sliding. So these are the three things actually happen during these three stages of the creep deformation. Okay, so first one is the deformation by slip. Deformation by slip. So I already said this process is happening at the elevated temperature. Okay, so what happened to the material? So for example, this is my material. This is my material, and this is the atoms arrangement inside the material. Okay, and this is the grain boundary. This one is a grain boundary. So when the temperature is increased, what happened to the atoms? Atoms in this sambhavikkum? Anyone? When I increase the temperature, what happened to the atoms? Go to atoms now.
Kinetic energy increases.
Yes, atoms change from lower energy state to higher energy state. At a room temperature, the atoms actually in the lower energy state. Okay, there is no energy for the movement of atoms, but the creep deformation is happen at a elevated temperature. Okay, the temperature is almost half of the melting point of the material. Okay, so under this temperature, these atoms are at a higher energy state. So that means there is a more chance for the slip of this atom. Okay, under this high temperature. So the atoms have a more energy and they may try to slip from this position to another position. Okay, so that is first one. There is a chance for slipping or there is a chance for dislocation movement. dislocation movement. So thereby there will be a deformation by slipping. That is the first process or first structural change inside the material during the creep deformation. So this is because of the elevated temperature and the slip will be developed. Okay, so that is the first one. At a high temperature, new slip system become operative. Maybe under room temperature, in case of BCC, only tall slip systems are there. But under higher temperature, when we increase the temperature, new slip system will be developed. So atoms have more tendency for slip in the new slip system. That means the deformation will increase, or the grain boundary dislocation motion will be increased. Okay, so these are the things happen under elevated temperature during the creep deformation. And under critical resource stress is required for slip of these new planes at elevated temperature is much lower than that of low temperature. So slip occur easily at elevated temperature, which is major cause of creep. Okay, so for the slipping of, for example, for the slipping of this plane of atom under normal temperature, I may supply 10 Pascal load. Okay, 10 Pascal load has to supply for the slippage of this layer of atom against the bottom layer. But at an elevated temperature, what happened? The amount of stress, the critical resolved stress required for initiating the slip can be reduced from 10 Pascal to 5 Pascal. So at a very low stress level, we can move the plane of atoms with respect to the bottom layer. That is the things happen during the creep deformation. Okay, so it is very easy for slipping of the atoms at elevated temperature. So that is the first thing. Second thing is this one, subgrain formation. Subgrains are formed. So during the high temperature application, dislocation claims can occur rapidly. Already you know what is dislocation claim. What is the dislocation claim? Dislocation claim. So this is the dislocation claim. So this is my slip plane. This one is my slip plane. So this is my slip plane. This one. Okay, this one is my slip plane, and in this slip plane, this is my dislocation line, edge dislocation line. So this dislocation is moving in this direction along the slip plane. Okay, so when a precipitate position in the slip plane, this dislocation cannot move further from this point towards this direction. Okay, because this precipitate actually block the movement of the edge dislocation. So dislocation cannot move further in the forward direction. So what happened? These atoms in the adjacent portions of this precipitate trying to climb up into the next layer of atoms. Okay, by the diffusion of atom. So here for this climb up, the temperature is a very favorable one, because here the temperature is elevated temperature, higher temperature. So the diffusion tendency of the atom will be very high under high temperature. So the atoms in around the region of this precipitate trying to climb up into the top layer of the atom. So that is the climbing of the edge dislocation. So this climbing will occur during the creep deformation. Okay. So that is the second. During the high temperature application, dislocation climb can occur very rapidly, because under high temperature, the atom's energy is very high. So there is a chance for higher diffusion for the atoms under this high temperature. Okay, so this dislocation rearrange themselves into low angled boundary. So by this climbing up and climbing down, and by the diffusion process, initial dislocations, this dislocations, initial dislocations have a chance to form a low angled boundary. They rearrange and form a low angled boundary. Okay, and these crystal regions formed by their sub boundaries are called subgrains. So initially these are the 3 grains, 4 grains in this material. But this rearrangement of dislocations by means of this climb up and climb down, new grains, subgrains are formed. Initially there are only 4 grains, but such type of subgrains are formed inside the material. Okay, so subgrains are formed inside the material, and these subgrains are actually, compared to the grain boundary, the subgrain boundary is not very strong. Okay, compared to the initial grain boundary, the subgrain boundary is not strong. That is only a very low angled boundary. Okay, so there is a chance for the it is a less capable for the preventing the dislocation motion. Okay, and that is a subgrain formation in the during the creep deformation. So that is the second structural change. Subgrains are formed inside the material. And how these subgrains are formed? The subgrains are formed by the rearrangement of dislocation by means of climbing up and climbing down of dislocation. So that is only happen in the elevated temperature. So that is the second process happen during the creep. And third one is the grain boundary sliding. Third thing is grain boundary sliding. So what is grain boundary sliding? So this is the grain boundary of a. So this is my crystal, a polycrystalline material. Okay, this is my polycrystalline material, and this is the such a grain boundary. There are 3 grains in this. Okay, so this is the grain. This is my grain 1. This is my grain 2, and this one is the grain 3. Okay, and this is my grain boundary 1, 2. That is separating grain 1 and 2. This is grain boundary 1, 3, and this is grain boundary 2, 3. Okay, so what is happening during the creep deformation? Grain boundary sliding. What is grain boundary sliding? So for showing the grain boundary sliding, I am drawing 3 lines here. 3 lines here. Okay, I am drawing 3 lines. So after creep deformation, during the creep deformation, there will be a grain boundary sliding. That means in this case, this grain boundary moving upward. Okay, this grain, the grain 2 along with the grain boundary will move upward by means of sliding. Okay, so by means of this sliding, this grain and the grain boundary move upward. So these lines, initially it was a straight line connecting this grain 1 and grain 2, and it is split into 2 lines similarly. So that means this portion move upward with respect to the grain 3. Okay, so similarly this one also. So this line is break into 2, and this region is move upward. Okay, so that is the grain boundary sliding. So this type of sliding may occur during this creep deformation. Okay, so that is also happen at an elevated temperature. So when the temperature is greater than 0.5 Tm, the grain boundary is actually very become very weaker, because in the grain boundary region, we know in the grain boundary region the atoms are less oriented, or is not strong bonded. Okay, it's a very weak. Initially it is very weak. At a higher temperature, again this atom got higher energy. Okay, so there is a chance for the movement of atoms along the grain boundary. So that is the reason for this type of grain boundary sliding at elevated temperature. Okay, so the grains will slide with respect to another. That is also another structure change during the creep deformation. So these are the three structure change during the creep deformation. Any doubt? എന്തെങ്കിലും ഡൗട്ട് ഉണ്ടോ? എന്തെങ്കിലും ഡൗട്ട് ഉണ്ടോ?
ഇല്ല സർ.
ജോയൽ ഇതൊന്ന് എക്സ്പ്ലെയിൻ ചെയ്ത് എന്താ വാട്ട് ഈസ് ഗ്രെയിൻ ബൗണ്ടറി സോറി സ്ട്രക്ചർ ചേഞ്ച് ഡ്യൂറിങ് ക്രീപ്പ്. ജോയൽ. ജോയൽ ആളില്ല ഇവിടെ.
ഹലോ സാർ.
എക്സ്പ്ലെയിൻ ചെയ്തേ.
സാർ ശ്രദ്ധിച്ചില്ല.
എന്തുകൊണ്ട് ശ്രദ്ധിച്ചില്ല? ഈ 4639 ആയത് എന്തുകൊണ്ടാ? ഈ 52 ആയിട്ടുള്ള ബാക്കിയുള്ളവരില്ലേ, ഈ 52 കഴിഞ്ഞിട്ടുള്ള ബാക്കിയുള്ളവരില്ലേ, അവരിന്ന് എനിക്ക് ഈ മൊഡ്യൂൾ 5 ഫുള്ള് വോയിസ് ക്ലിപ്പായിട്ട് അയക്കണം കേട്ടോ. മനസ്സിലായില്ലേ? തുടക്കത്തിൽ ഉണ്ടായിരുന്ന 52 ഞാൻ അവരുടെ ലിസ്റ്റ് ഇന്ന് അയച്ചേക്കാം. അവരെല്ലാവരും എനിക്ക് ഇതിന്റെ ഫുൾ വീഡിയോ, അതായത് ഇതുവരെ മൊഡ്യൂൾ 5 എവിടെ വരെ പഠിപ്പിച്ചോ അതിന്റെ വോയിസ് ക്ലിപ്പ് അയക്കണം കേട്ടോ, ഇൻക്ലൂഡിങ് ജോയൽ. മഞ്ജിത്ത്, മഞ്ജിത്ത്, മഞ്ജിത്ത് ഇവിടെ ഇല്ലേ?